So this equation right here, this expression, describes the probability that a system has a specific value of the momentum for a specific particle. Okay? And so just to kind of give you a visual sort of representation of what this result is, here's what the Maxwell-Boltzmann distribution looks like at different temperatures. Okay? All right, and so from this plot, we see that the Maxwell-Boltzmann distribution, it has a Gaussian shape, right? So it's monomodal, and also it's symmetric, right? So this side is a mirror image of the right-hand side. And so what that means is, because if we look at the x-axis here, which is momentum, which goes in both the negative and the positive direction, right? Because it's symmetric, that tells us that in terms of this particles within the system, there's no flow in any direction, right? Because the probability that its momentum has some negative value is going to be canceled out by the probability that the particle has a momentum going in the equal but opposite direction. Okay? All right. Furthermore, we see that as we increase temperature, the distribution gets flatter and flatter, right? Such that momentums in the more extreme sides of the distribution, their probability increases. Okay? And so to kind of summarize or write this out, Maxwell-Boltzmann distribution is Gaussian and symmetric. There's no flow in any direction. And then also, here we just focused on the influence of momentum, right? We didn't have to worry about the impact of the potential term of the Hamiltonian. And so, because this distribution is independent of the potential, it's general, right? And it just applies to any system. Right? All right, and so there's two ways that you can interpret the Maxwell-Boltzmann distribution. Okay? Where you could either think of it in terms of time, so it's a temporal distribution, so it gives the probability distribution of a single particle over a long period of time, right? So that, here you say, if I track a single particle over some period of time, its probability could either be here, or its probability that has a certain momentum, its momentum could be here, or here, or here, right? And that the probability that I would find the particle with a particular momentum would just follow this distribution. That's one way to interpret the Maxwell-Boltzmann distribution. Another way to interpret it is that it gives the distribution not of one particle, but of many particles at a single instant in time. Right? Such that this distribution tells you there's a probability of finding a particle with this momentum, or this momentum, or this one, right? That's another way to interpret the distribution. Of course, as we remember from before, that if we're dealing with an ergodic system, then both interpretations are equal and valid. So both interpretations are valid. Right? They'd be equal to one another, and that would indicate that the system is at equilibrium. Okay. Um, since with the Maxwell distribution we have these probabilities, we could also use it to calculate the average momentum of the system. And so that, all we'd have to do is just take the first moment, which would be described like this. So this is accounting for all directions, right? And we could simplify it down to this form, since each of the directions are independent of one another. So it would end up just looking like this. And this average momentum term here would be described, by the first moment. Okay, where you have your px squared there, and for the probability, plug in the Maxwell-Boltzmann distribution. If you go through the math, which initially looks intimidating, go through the math, you'll find that it actually ends up in a very elegant form, that the average momentum is just equal to n 3/2 nkbt. Okay? Alright, so that's how you find the average momentum of the system, or the average kinetic energy of the system. One last thing I want to point out is, with the momentum, we found that it's symmetric. Right? And that's because you could have negative or positive momentum. But if we think about the speed that a molecule is moving, with speed you're just looking at the magnitude of the velocity, not the direction. So as a result, we find that as we go from momentum to speed, that the distribution is not symmetric anymore. Rather, it starts at 0, and then it goes up, there's some maximum, and then it keeps increasing, right? And so here we find that as we increase temperature, the peak of our speed distribution goes to higher and higher speeds, right?